Everyone, today we want to welcome to this class. I want to be discussing on topological spaces. What's called about topological spaces? And let's look at the definition of topological spaces. What are topological spaces? What does it mean? Now it means that if you have a non-empty set X and you have a family, that is the collection of the subset of this X, such that the following conditions are satisfied. Number one, when you are picking X, an empty set and member of that family, that is of this tau. Then number two, for any arbitrary element in this tau, so that your alpha is from what? From here. Then there must be what? Arbitrary union on it, that is of this one of A alpha also must be in that tau. Then the third condition that I have to take note is that for any finite members of tau, where your high is ranging from 1 less or equal to high less or equal to k, then you have what? Finite intersection r equal to 1 to k of what? A high also must be a member of that subconnection or a member of that family. And when you look at it physically now, it is when all these three conditions are satisfied, then you can now call this family, this tau, a what? Is a topology. So this tau is now referred as what? A topology, where you now have the x comma tau, it refers to as what? It's called what? Topological. It's called topological space. It's called a topological space. So that is what we are talking about, a topological space. A family, a collection of X is said to be a topology if the following conditions are satisfied. Number one, S, the whole set and the empty set are member of that topology. Then for any arbitrary element in that subconnection or in that topology, then there must be what? Union of arbitrary values must be. That's why I can say that the union of any number of sets in tau belongs to tau. The union of any number of sets in tau. No, this is a member in this tau now. So the union of it also belongs to tau. Then also the intersection of any finite number of elements in that tau also is intersection of what will also be in that tau. For any finite number of elements you have in now, the intersection also must also be in that tau. Then this tau is called a topology. Now, there's another thing I want to note that when you have a topology like this, then every member, that is, you can say that the members of tau are called, and they are called what? They are called tau open sets, or you can simply call it what? They are open what? Open sets. So that is every member of this topology here, of this topology now, is referred as what? Tau open set, or you can simply call it what? It's an open set. They are also an open set. Now let's look at this example now. For instance, let's check this example out and let's see whether it actually forms a topology or not. Either for a topology or not. No. Consider example now. Talk about example now. Let's see. Consider the following classes. Of subsets of X. Let's say A, B, C, D, and what? And this E. Now, let's check. I am given a collection of tau 1 now. Let me give you a set of X, empty set. We have a set A. We have another set A, D. We have A, C, D, and we have what? B, C, D, E. Now, our question now is this. will this one form a topology or not? So that is a question we have to check whether it's going to be a topology or it's not going to be a topology. So for it to be a topology now, it must satisfy these three next conditions. And to do that now, when we look at it critically now, we can see obviously from there, condition number one, the first condition number one is what? Is odd. That is, you can see that x, empty set, they are member of that what? Of that topology, of this tower. You can see that it's also member here now. Now let's pick any arbitrary union now. If I pick any arbitrary here for tau 2 now, if I pick any arbitrary union now, if I pick A union, look at this for example now, set A union what? C, D, what do you have? A, C, D. And A, C, D is also a member here which belongs to what? In that tuple, in that tower, in that subclasses of subset. Now, you can see it's there now. So, then if I pick another one, if you pick A union this, you get it back. A, set A union this, you get A, B, C, D, E. That gives us the whole set X back, which also a member of that topology. Then number two is that you pick CD union with this one. What do you have? Union with this one, what do you have? We have ACD. You have ACD back, which also a member of that topology. If you pick CD union with this one, we have BCDE, which also a member of that one. So it satisfies the second condition. Then the third condition now, let's say T3. The third condition is that for any finite, look at it, any finite intersection, or not finite intersection, any finite member of that topology, then the intersection of any finite member also must be in that subclass of subset, that is in that topology. Now let's pick it out. So if you pick A, look at it now. If I pick A intersection CD, what do you have? That's an empty set, which also a member of that topology. Then if you pick A intersection this, that's singularity A, also a member of that topology. If you pick A intersection BCD, we have an empty set, which also a member of that topology. So it shows that therefore the three conditions are satisfied. Therefore, that one is a topology. So that is why we can show that this that one now is a topology. Once you verify all the three conditions and they are satisfied, then you can call it a topology. I hope you are following now. Good. Now let's pick another subclasses now. Let me pick another subclasses of topology, whether it's going to give us a topology or not. I want to let's check together. Let's check that. Now look at this one now. Look at this tau 2. Let's say I have another topology tau. Let's say I have this x, empty set, set A, CD, then ACD, together with what? BCD. So I have this one now. Now let me ask a question now. Will this one form a topology? That's the first question I ask yourself. Will this one form a topology? Now let's check it. Now, condition number 1 is obviously true. Condition number 1 is what? It is true because I find that X and empty set are member of that topology. You can see that they are member of that topology because you can see the whole set X and the empty set is there. Now, let's check number 2. Let's say condition 2 is condition number 2. Does it hold? Condition 2, does it hold? Let's check it together. Now, condition 2 was saying that union. If I pick A union CD, I have what? ACD. That is true, If I pick A union ACD, you still have what? ACD, which is also a member of that topology. If I pick A union BCD, we have what? ABCD. Now, look at this. I see something now. A union what? BCD. What do you have? I have A, B, C, D. So you can see that gives us what? A, B, C, D. And this A, B, C, D that you obtain here, this guy is not a member of that topology. You can see that this one is not in this topology now. So once one of the conditions is not satisfied, definitely it is not a topology. Therefore, Therefore, I can say that this tau 2 is not a topology because it does not satisfy. It fails one of the conditions. How we are following now? Good. Now, let's still check another one before we proceed. Let's still check another topology whether that will also give us a topology or not. That will give a topology or not. Let's check it again. Now, look at this one. Look at this. Let me give you this topology now. You have x, empty set, set A, C, D. Now A, C, D with together with what? A, B, D, E. Look at this member of this topology now. With this one form a topology, let's check. Condition 1 is true. Empty set, no. Condition 1 is always true. I think I say that what? X and no set of what? Is a member of that one now. Now let's check condition 2. Let's check whether condition 2 is also odd. To check condition 2 now, A union this. ACD, which is M. A union ACD. What do you have? A union what? ACD. Give us what? ACD. CD union ACD. Also give us that. This one union this. I have what? A, B, C, D, E. So this one union this. A, B, C, D, E. So that means condition 2 is also what? Also odd. You can see that. You can find arbitral union of this. Of omega of A and is also a tau. Now let's check the intersection now. Let's check the intersection now. If I check the intersection now, A intersection this empty set is here, Abi. A intersection this set A is also here. A intersection this A is also here. C intersection CD is here, Abi. CD intersection. Look at this one now. I got something here. A C comma D intersection A, B, D, E. What do you have? You obtain something like D, and D is not a member of that family. So therefore, this tau is not a topology. It's not a topology. So that is how we can show that that one is not what they are not topology, and all this cannot be an open set. So now let's check. Let's proceed to what we have been discussing so far. Now, I do want to let us look at something very important, and that is called open set and closed set. Open what? Open set and what? And closed set of a topology. Now, previously I said that the members of the topology are called what? Tau open set. Or simply call what? An open set. So open set, let's say let X be a what? Be a topological space. Abi, where tau is what? Is a topology. Thus, the members of tau are called what? They are called tau open what? Open sets, or simply open what? Open set. So or simply what? Open set. So now in the first example that I gave out, now we said that we are given like let X be equal to what? A, B, C, D, E. I know that. And which has a topology of S empty set. Then we have A, we have C comma D, then we have ACD, and then we have what? B, C, D, E. So these are what we have. Now, each of these terms, each of these sets that you have here in this topology, they are called what? An open set. That is, we can say that this set A is what? Is an open set. Then C comma D is a what? Open set. These are the open set we have now. A, C, D, they are what? It's also an open set. Then B, C, D, E is also what? An open set. Then this set on itself is what? Is an open set. and then lastly, empty is also what? Is also an open set. So each member of this one diverges what? Than open, diverges as open set. So with that now we can now look for a result. Can report a result here. A result was saying that he said, let's before we go to that result, there's something I want us to actually look into also. I want us to look into. Now there's something we called discrete topology. Oh, before I go to that, there's something called closed set. Now, before I move on to some other classes of topology. Now, what is about a closed set? Now, when you know that each member of this one, they are what? They are open set now. Now, what is about a closed set? What does you understand by a closed set? What do you understand by a closed set? Now, what does it really mean? It means that when you look at, he said, let X, look at it too. Let X be a topological space. I know that. Let it be a topological space. A subset A of X is a closed set. Is a what? Is a closed set. It's a closed set if it complements. That is, complement of that A is what? Is an open set. If complement of that A is what? Is an open set. Okay? You know, we said that an open set is a member of a topology. Now, we now say that let X be a topological space. So a subset A of X is a closed set if its complement is an open set. That is, look at it. So you know the previous example I gave. Let's look at it. You know, we have tau to be this X empty set A C, D. Then we have A C D together with what? B C D E. So this is an open set, Abi. Now we're not saying that okay, if I find the complement of each of these members I have here. So if I find the complement of it, and that complement of that set I obtained, they are also a member of this topology, then that set A is over to what? A closed set. For instance, you know, this is a topology on its own. I mean, this is a topology for X. You know, we have our X is given as A, B, C, D, E. I know that this is an X now. Now, what are the closed set here? Now, your closed set are what? The closed set of X, the closed set of X are what? They are now give us as this. That is, if I pick complement of this one, give me what? Empty set, Abi. Complement of this one, give me what? Give me X. I got that. Complement of set A will give us what? B, C, D, E. Can you see that? Now, the complement of CD, what do you have? Complement of CD will give us A, B, E. I got that. A, B. Complement of that will give us what? A, B, E. Then, complement of A, C, D. What do you have? Complement of A, B, C, D give us what? B, E. Then the complement of B, C, D, E give us what? Give us A. So all these ones that are just obtained, they are called what? They are called the closed set. They are called the closed set. Now, yeah, the closed set, therefore, the closed sets are, we are now having as what? We have this empty set X on its own. I got that. Then I have B, C, D, E. Then I have A, B, E. Then I have B, E. That's what without set A. So all these ones are what? But there's something I want to take note here. You know that there are subset of X such that BCDE, look at it, BCDE now, which are both open and closed, and there are subset of X such that AB, which are neither open nor closed. So despite that, that's at the closed set that we have. That's how you can obtain the closed set for a topology. Now, in that line, we can now redefine topological space in terms of what? Closed set. That's we can define topological space in terms of closed set. How do we do that? And that comes up with a theorem. Look at the theorem now. It comes up with a theorem that is now number one. Look at this theorem now. It comes with a theorem, and theorem says that let X be in topological space. Be topological space now. I got that. So then the class of closed sets, closed subsets of X possess the following properties. What are the number one? You have your X and that of empty set are what? They are closed. So you have X and that of set are what? They are closed. Two, we have the intersection of any arbitrary set. Any arbitrary closed set is what? Is closed. That's that. So the intersection of any arbitrary closed set, closed set is what? Is closed. Then the third one, the union of any finite closed set is also closed. So these are the way you can also redefine your topological space in terms of what? Of closed set. So you have to know that these theorems are true, because by the time you take you use the assumption, by the time you take complement of this one, will give you this